Hi guys, and welcome back to my channel. In this video we're going to be talking about the quantization of energy levels in atoms. In the last video we talked about Planck and how he sort of brought about the quantum theory, but he focused mainly on electromagnetic radiation. So we talked about his idea that electromagnetic radiation and the energy transferred by it was transferred by discrete sort of packets of energy. There were these photons that carried discrete amounts of energy, and these were the sort of smallest amounts of energy you could transfer using electromagnetic radiation. Now in this video we'll talk more about quantization of energy levels in atoms and how there's discrete electronic energy levels in atoms such as the hydrogen atom, and this was sort of the idea that Bohr developed. So let's get right into it. So what exactly was the first main piece of evidence for these discrete energy levels? The main piece of evidence that we saw was spectral lines of elements. So this happens with any element, not just hydrogen, but in this video we'll be focusing mainly on hydrogen and other isoelectronic atoms. So let's talk about spectral lines. How do spectral lines arise, right? Basically, these are discrete frequencies of light that are absorbed by hydrogen. So hydrogen does not just absorb every frequency of light, it absorbs these sort of discrete, specific frequencies of light. So why does it pick and choose what frequencies of light to absorb? This comes from the discrete electronic energy levels in atoms. So there's two really key series that you need to know for USNCO and for general chemistry knowledge. The two key series are the Balmer series and the Lyman series, and I'll talk about these more on the next slide. But basically, the Balmer series arises from frequencies of light that are either absorbed or emitted by coming to the n equals 2 state of the atom. The Lyman series are frequencies of light that have to do with the n equals 1 state of the atom, and I'll talk more about this on the next slide with a sort of picture so that it's easy to wrap your head around. So what was the Bohr frequency condition? The Bohr frequency condition, he basically said that the energy of the photons that are absorbed, so the specific frequencies of the light, have to exactly equal the difference in energy between the two distinct energy levels in each atom. So let's go to the next slide and I'll sort of show what I'm talking about with the picture of the hydrogen atom. Okay, so on the right you can see that I have a little picture of a basic idea of what the hydrogen atom looks like. So let's take the Lyman series first. The Lyman series has to do when an electron at the n equals 1 state absorbs a certain frequency and goes up to the n equals 2, n equals 3, or n equals 4 states. So any of these sort of jumps up is part of the Lyman series. We can also have emissions as part of the Lyman series, when something from the n equals 2 or n equals 3 or n equals 4 or n equals 5, etc. jumps back down to the n equals 1 state. And on the last slide we could sort of see that the Lyman series generally emits and absorbs light in the UV part of the electromagnetic spectrum. Now what is the Balmer series, right? The Balmer series has to do with the n equals 2 state. So we can see there's an electron drawn in right here. If this absorbed a certain frequency of light and moved up to the n equals 3 or n equals 4 state, these frequencies of light would be represented in the Balmer series. And similarly, we can have the emission lines as well. If the n equals 3 or n equals 4 jumped back down to the n equals 2 states, these would also be the same frequencies that are represented in the Balmer series. Now let's talk about the energy levels in the hydrogen atom. So we just talked about how there's discrete energy levels and how these correspond to spectral lines. But what even are the energy levels? What is the energy of these different levels, right? These discrete energy levels are given by the principal quantum number, which we call n. And you've probably heard of this in your AP Chem class, where you talk a little bit just very qualitatively about quantum numbers. So the principal quantum number, or n, gives the energy level in our hydrogen atom. And we can describe the energy levels, E sub n, as equal to negative h, which is Planck's constant, times r, which is another constant called Rydberg's constant, divided by n squared. So basically your energy levels in your hydrogen atom are inversely proportional to n squared. That's the key fact to remember. And we'll talk more about Rydberg's constant in the next video, where I'll actually derive it for you, and based on the principle that angular momentum is quantized. But I won't get into that now. We'll talk about that more in the next video. So if we use this energy level equation, we can derive what the frequencies that should be absorbed are. If we take these two energy levels and call the first one that we start at N1 and the second one that we end at N2, right? And if we subtract these energies and then divide by h, because we know that E equals h times the frequency, right? So if we take the difference in energy levels and divide by Planck's constant, we should be able to figure out what the frequency that is absorbed by these atoms are, right? And that's what this equation gives us. It tells us that the frequency absorbed is Rydberg's constant, which and Planck's constant is eliminated because we divide by h, times the difference in the inverse squares of your energy levels, of your principal quantum numbers. And again, we'll talk about Rydberg's constant in the next video, and we'll derive it in the next video. So now let's talk about isoelectronic atoms, such as helium plus or C5 plus. So I guess these aren't really atoms, sorry, these are isoelectronic ions. They have a really similar equation for energy levels because their ions basically look the same as hydrogen, except instead of one proton in the nucleus, we have more protons in the nucleus. So what should this do to the energy levels? It should reduce the energy of our electron. Because why should it reduce the energy of our electron? Because now the electron has a stronger attraction to the nucleus because there's more protons there, right? And positive and negative charges attract each other. So the more protons there are, this electron will be in a lower energy level, or the energy levels will have a lower energy because there is a stronger attraction between the protons and the electron is happier, right? So now let's describe the energy levels a little more quantitatively, right? So if we look at this equation here, we see that our E sub n, so again we describe our energy levels with our principal quantum number, E sub n is equal to negative z squared h times r over n squared. So this basically looks exactly like our hydrogen atom equation for the energy levels, except we now have a z squared term. What is z, right? That doesn't make any sense. What is z? Z is our nuclear charge in the atom. So for example, in helium, right, now we don't have just one proton, like in hydrogen, we have two protons. So our z would be 2 rather than 1. So if we look at our equation, right, our energy level is multiplied by z squared. So we actually have a factor of 4 that it's being multiplied by. So the energy of the helium atom will be 4 times more negative than the energy levels in the hydrogen atom. This is why it's like so much more stable, right? So why is there 2 factors of z? Let's sort of give a little intuition behind this. One z factor comes from the higher field that's created. Why is there a higher field? Because there's more protons in the nucleus. That creates a stronger electric field, a stronger electric attraction on the electron. The other z factor comes from the fact that the electron is now closer to the nucleus, right? Why is it closer to the nucleus? Again, there's a stronger pull. The protons are pulling on the electron more strongly, and this causes the electron to be closer to the nucleus. And that means that it's going to be a lower energy, because the lower distance that the protons and the electrons are separated by, the happier the electron is. So that's why there's sort of 2 factors of this z in our energy equation. Now let's talk about ionization. What is ionization, right? Ionization is when we say like an electron is totally removed from the atom. So what does that mean when we look at our n equals 1, n equals 2, n equals 3, and these sort of states? When an electron goes to the n equals infinity state, right, that is when we have ionization. So for example, if we have a hydrogen atom, right? In our ground state means our electron is in the n equals 1 state. Then the ionization energy it's going to take is whatever it takes for me to go from the n equals 1 state to the n equals infinity state. And n equals infinity, if we look at our energy levels, right? Because E sub infinity, equals negative hr over n squared, but n is infinity. And this basically will lead to an energy level of 0. That makes sense, because if the electron is infinitely far away from the nucleus, there should be no sort of potential energy, no sort of stabilization factor that comes from this, right? We're basically taking the electron so far away that there's no interaction, so there shouldn't be any negative energy, there shouldn't be any stabilization factor that comes from ionization. So this is what ionization really means. It's when we have an electron that goes to the n equals infinity state. All right, now let's talk a little bit about energy degeneracies in hydrogen and isoelectronic ions. So when I talk about hydrogen and isoelectronic ions, they're basically the same thing, except the isoelectronic ions have a higher nuclear charge. So let's discuss these degeneracies. In our n equals 1 state in our hydrogen atom, right, we only have one orbital, and that's our 1s orbital. And this should be sort of familiar to you from AP Chem, right? But in our n equals 2 state, we're able to fit 8 electrons. Each orbital only has 2 electrons, right? So that means there's 4 different degenerate orbitals that have the same energy. And this again should be familiar from AP Chem. We have our 2s orbital, and we have 3 2p orbitals. And you might be saying, wait, aren't 2p orbitals generally higher in energy than 2s orbitals? We usually fill our 2s orbitals before we fill our 2p orbitals, right? But no, they're not always higher in energy. The higher in energy comes due to what we call shielding, when we have more than one electron. And I'll talk about this in a future video, but I just want you to be aware that when we only have one electron, these orbitals are actually degenerate. Our 2s and our 2p orbitals have the same energy. Next, if we look at our n equals 3 orbital, we say that there's 18 electrons that can fit here, right? That means we need 9 degenerate orbitals, and this comes from our 3s orbital, our 3p orbitals, and our 3d orbitals. And again, these are all degenerate in the hydrogen atom, and the differences in energies that we usually see when we look at these orbitals come from something called shielding when there's multiple electrons in the atom. So that's basically what I've written here. Due to shielding in atoms with more than one electron, our energy of 2s is not equal to the energy of 2p, and our energy of 2s is actually less than our energy of 2p, and this is why you fill the 2s orbitals before you fill the 2p orbitals when you're writing general electron configurations. But for one electron atoms, the n quantum number completely defines the energy levels, and therefore all we need to determine the energy state of the electron is the n quantum number, right? This is sort of what we talked about before, and this is why our energy levels of 2s is equal to the 2p's in a single electron atom or ion. So now I just want to discuss some general things to know about quantum theory that are very they're very much the pillars of quantum theory, both wave-particle duality and the uncertainty principle. So in the previous video, we talked about how Planck sort of discussed how light behaves as both a particle and a wave, and we talked about the photoelectric effect and how Einstein showed that light did behave sort of like a stream of photons. But before, we also knew that light behaved as a wave because we saw that we had diffraction effects and constructive and destructive interference effects. So de Broglie kind of said, if light can behave as a wave, right, and a particle, why doesn't matter also behave as a wave and a particle? There should always be some sort of wave-particle duality. And so he came up with the idea of a matter wave, that every piece of matter, along with being sort of like a particle, like how we generally think of matter, there's also a wave that is associated with that particle. And the wavelength of that wave is given by his equation. It's given by Planck's constant divided by the momentum of that particle. So if you try calculating this for anything, macroscopic, right? If you try calculating this for any, like a baseball or something like that, you'll realize that the lambda that you calculate is really, really, really small. And this should make sense, right? Because we don't observe matter acting as a wave on a daily basis. It makes sense that the lambda would be really, really, really small and sort of undetectable. Now I want to show just how, for light, this equation also agrees with what we previously know about the frequency and wavelength relation of light. So for light, we have this equation that the energy of light equals the momentum times the speed of light. If we rearrange this equation, we get that the momentum equals the energy divided by the speed of light. And Planck, right, because of Planck, we know that the energy of light is the same thing as Planck's constant times the frequency of light. So now we have this equation for the momentum of light, Planck's constant times the frequency divided by the speed of light. Now if we substitute this into the de Broglie equation, right, lambda equals our Planck's constant divided by our momentum of light, and this gets us that lambda equals the speed of light divided by the frequency of light, and this is exactly what we know from AP Chem or any previous chem knowledge, right? So this agrees with our previous intuition, so this should make us happy, right? The de Broglie equation works for not only both matter, but also for electromagnetic radiation. Now I just want to talk about the Heisenberg uncertainty principle and mainly the intuition behind it. The equation is listed here, and it basically says that the error in our momentum measurement times the error in our position measurement must be greater than or equal to some constant. And this constant is half times the reduced Planck's constant, where the reduced Planck's constant is Planck's constant divided by 2 pi. This exact equation is not very relevant for USNCO or really for much at all, apart from a rigorous quantum chemistry course. But the intuition behind this equation is really important. Basically what this means is that the more we know about momentum, right, say our error for momentum is really small, that means the less we have to know about our position because the product of these errors must be greater than or equal to some certain baseline amount. It also means that the more we know about the position, the less we know about the momentum or the speed of the particle. So this is a really important sort of intuition background to have, and it's not something that has to do with what our measurements are. It just has to do with how the world works. And we can never get a more precise measurement. We can never know perfectly what the position and the momentum of a particle is at a certain point in time. So that's basically all I wanted to cover today. Thank you for watching this video, and I hope this was helpful, and I hope you learned something from it. So I'll see you in the next one.